In this problem, we are asked to calculate the pH of a 3.8 molar solution of boric acid. All we are given is the acid dissociation constant, or Ka, of boric acid, which is 5.8 times 10 to the minus 10. The first step is to identify all of the species present in solution that may affect its pH. Because boric is a weak acid, well, we know that weak acids ionize to a small extent. So at equilibrium, the major species present in the dissociation of boric acid are going to be non-ionized boric acid, hydronium, and the conjugate base of the boric acid. And that is what we have here in a solution. So imagine we have this beaker here, and in this beaker we have boric acid at a concentration of 3.8 molar. Now, another major species that will be present is, of course, water. But we're going to ignore water, and we're going to ignore the autoionization of water because in reality, the amount of hydronium ions that we will get in solution as a result of the autoionization of water is very small. So the majority of the H+ ions present in solution will be from the boric acid itself. So we're going to, again, ignore water. Our next step is to use an ice table to express the equilibrium concentrations of these major species. So again, we've identified these major species as boric acid, hydronium, and the conjugate base. So what is the initial molar concentration of boric acid? Well, they tell us here. It is 3.8 molar. The initial concentration of hydronium from the dissociation of boric acid would be 0, and the initial concentration of the conjugate base would be 0. Now we know that this weak acid, boric acid, is going to ionize. And so we're going to let the letter X stand for the change in concentrations. So we're going to have a change in concentration of boric acid as this reaction moves toward equilibrium. It's going to be negative X. We're going to have a change in concentration of H+. It's going to be plus X. And we're going to have a change in concentration of this conjugate base. It's going to be plus X. Now this dissociation reaction equation written as is balanced. And so what is the equilibrium concentration of each of these species equal to? Well, according to our ice table, the equilibrium concentration of boric acid is going to be equal to 3.8 minus X. I'm just adding straight down. Here, the equilibrium concentration of hydronium ions is going to be equal to whatever X is. And the equilibrium concentration of our conjugate base is going to be equal to whatever X is as well. So you may get a hint that they're asking us to find the pH of this solution. How do you find pH again? pH is equal to the negative log of the hydronium ion concentration. So what we're doing is we're trying to find X so that we can find this, and from this, find pH. Now from the ice table, we can write the equilibrium expression for this ionization, the ionization of boric acid. Well, the acid ionization constant, or Ka, is going to be equal to the concentration of H+ times the concentration of this conjugate base divided by the concentration of boric acid. So what we want to do is we want to substitute the values that we can here in this equilibrium expression. So can we substitute Ka? Well, yes, we can. They give us the Ka of boric acid. It is 5.8 times 10 to the minus 10. Well, that's going to be equal to, well, what do we substitute the concentration of H+ with? Well, let's go back to our ice table. At equilibrium, which is what this is, again, the equilibrium expression for the ionization of boric acid. So at equilibrium, what is the concentration of H+ equal to? Well, at our ice table, we have determined that the equilibrium concentration of H+ is equal to X. So I'm going to place X here. Well, at equilibrium, what is the molar concentration of the conjugate base equal to? This conjugate base. Well, if I go back here, it's also equal to x. So x times x over, at equilibrium, this is the equilibrium constant expression. At equilibrium, what is the concentration of boric acid, H3BO3, equal to? Well, we determined here in our ice table that it is 3.8 minus x. So I'm going to put 3.8 minus x here. And so if I simplify this, we have that the Ka of boric acid is equal to x squared divided by 3.8 minus x. Now, you all are going to like these problems from this topic because there's a shortcut that we can use to solve for x, which will allow us to work around having to use the quadratic expression. Now, this shortcut doesn't always work, but it's a good idea to start with the shortcut and then check it to see if the shortcut assumption is valid. Now, here our Ka is really small, 5.8 times 10 to the minus 10. So the chances that the shortcut will work are fairly high. Well, how does the shortcut work? Well, the shortcut works like this. Because this Ka is so small, we can expect that x, the amount that the concentration is going to change from the initial concentration to the equilibrium concentration, we can expect that x is going to be very, very, very small. In fact, x is going to be so small that if I subtract x from 3.8, well, after I do that, I'm going to see that the answer I get is going to be pretty much 3.8, what I started with. So we are assuming that x is going to be very, very small. And so the shortcut method makes the assumption that x is so small that if I subtract it from 3.8, I'm still going to have pretty much 3.8. So this shortcut method is called the approximation method. And so to use it, I'll just continue on working this problem. And I will approximate x by saying that it's so small, there's no point even subtracting x from 3.8. And so now I can solve for x without having to use the quadratic formula. And so now, to solve for x, I just bring 3.8 up, multiply both sides by 3.8, and here I get x squared is equal to a very small number, 2 times 10 to the negative 9. And to solve for x, I'm going to take the square root of both sides, and I get that x is equal to a very small number again. It's going to be 4.695 times 10 to the negative 5. So let's take this value for x that we obtained, and let's go back to our ice table. So now we have the information we need to find the equilibrium concentrations of our major species. Well, how do we do this? Well, we look at our ice table, we have obtained x, and so we plug x into what the equilibrium concentrations are equivalent to according to our ice table. So the equilibrium concentration of boric acid, according to our ice table, is equal to 3.8 minus x. So what is the equilibrium concentration of boric acid? Well, it's equal to 3.8 minus x, which was 4.695 times 10 to the minus 5. 4.695 times 10 to the minus 5. The equilibrium concentration of hydronium is equal to just simply x. So 4.695 times 10 to the minus 5. And the equilibrium concentration of the conjugate base is equal to just simply x. So 4.695 times 10 to the minus 5. So let's see what this value is here. And in my calculator, I get 3.7999 as my value. So before we move on and accept these as our answers, we want to make sure to double check the approximation method and see if it is valid. Well, how do we check the approximation to see if it's valid or not? We just take our value for x that we have. So we take our value for x, which is 4.695 times 10 to the minus 5, and we divide it by the original concentration, the initial concentration, 3.8. So this is the change in concentration, which is what x represents, the change, right? The change. And this is the initial. So change divided by initial times 100 to convert it to a percent. What do we get when we do this? I get 0.0012%. As long as this value right here, which is the change, or x divided by the initial concentration, as long as this value is less than 5%, then the assumption is valid. If this percentage is greater than 5%, that means that the assumption is not valid. And this is based off of what we know about Kas. So because this percentage is much less than 5%, then the approximation method, or the assumption that we make, is valid and we can use it. So to finish up this problem, I have to remember that they're asking me for pH, and pH is equal to the negative log of the hydronium ion concentration. Well, at equilibrium, the hydronium ion concentration in this solution is going to be this. So the pH is going to be equal to the negative log of that value, 4.695 times 10 to the minus 5. This will give me a pH of 4.3, rounded to 1 decimal place like they asked. And that will be my answer.